So, first of all, I'd like to thank the organizer for the invitation to talk about machine learning in theoretical physics. And so I have prepared these slides, but I have thinking about isolating the problem to high energy physics because it's probably one of the most interesting fields that where you can apply. Now, when we start looking at applications in TH, probably the first question that you can ask is what exactly it means machine learning in high energy physics now, for theory. What's the status and what are the most important applications that we have today. And in fact, this is not quite simple because you see there are a lot of projects involving particle physics and experimental field and data analysis, but when talking about theoretical physics, it's complicated. So I think we can classify the applications in theory into two levels. I call level 0, all the applications where we have computational techniques and tools. So this contains advanced numerical methods and applications, Monte Carlo event generators, and higher order correction. So all the techniques which are extremely important for the evaluation of observables that will be then compared to data. And these tools are very popular and may or may not use the machine learning techniques that we have seen in the previous talk. So we are talking about regression, classification, neural networks, and so on and so forth. And if we list some examples, we can see things like Monte Carlo output storage, subtraction schemes, the evaluation of loops and loop techniques, and many talks that you can see in the track 3 in the parallel section. So this is very important for the theoretical community, and it's really the cutting-edge technology that we have when evaluating Feynman diagrams and implementing the Monte Carlos. And then we have a second level that is more tricky to identify, and it is, let's say, machine learning in sensu stricto. So machine learning in the terms of the modern techniques that have been published in the past 10 years and also that have been developed in these few years. And we are talking about regression and classification, supervised learning, and two new items which are techniques for the uncertainty propagation and combination, and the so-called experimental mathematics. Now with TensorFlow and other libraries, many theoretical physicists, they are taking their problems and reverting the optimization problems in terms of these libraries and using machine learning techniques to obtain the results. But as you can see, the level 1 is really close to HEP experimental, no? Because many of these applications will require data. And it's very simple and very easy to find hybrid projects where you have the theoretical applications connected to the data. Here are some examples. When you talk about regression, you have the determination of the Parton structure. You have also the determination of fragmentation functions and Monte Carlo tunes. For example, the reweighting techniques to include the higher order corrections to Monte Carlo events. When talking about classification, we have these nice hybrid projects where you use deep convolutional neural networks for jet discrimination that you saw previously. And then we have the uncertainty estimation combination. One nice example is the PDF for LHC tools that have been published last year, together with higher order models to estimate the uncertainty of the Monte Carlos. And finally, for the experimental mathematics, you can think about the determination of the densities and the Monte Carlo integrations itself. These topics have been started several years ago, 10, 20 years ago with Garrido, and today they are also very, very relevant for the theoretical community when implementing Monte Carlos. So I cannot focus and talk about all these projects, but I would like to give you an idea of one of the most important projects and topics that we have in theoretical physics that in the past months and years obtained a very nice boost due to machine learning, and concerns the determination of the structure of hadrons, in particular for the proton. So the PDFs, the Parton distribution functions. So I will show you some details of the NNPDF methodology, which is recently used by several experiments and also theoretical computations. And then I will go through the PDF for LHC recommendation, showing step by step the different algorithms that have been constructed in order to generate a combination of PDF uncertainties and create a sort of compression of the information. So we can use and experiments and people can use without computing a large number of replicas. Okay, so let's start with PDFs. So what is a PDF? Just to summarize, PDFs are used every time you need to evaluate a hadronic cross-section. So you have an observable, in this case sigma, and we can write this cross-section in terms of a convolution between a hard cross-section, sigma hat, and the PDFs. So the PDFs are not calculable because they reflect the non-perturbative physics of confinement. So we needed to extract PDFs by comparing the theoretical predictions to the data. So PDFs, they depend, so you see in blue, depends on I, which is the parton flavor. You have the quarks and gluons, the momentum fraction, X, and the energy scale, M. And this information needs to be learned from data. If you rewrite this problem in terms of a machine learning technique or optimization problem, you see that we have to determine F from a convolution between X by comparing to Y. And we are not talking about a deep big data problem, because usually, as today, if you collect all the last 30 years of measurements, we have around 4,000 data points. So this is not too much, but in the next 5 to 10 years, we will get a lot of new data from LHC. So this problem will start to reach some dimensions with larger than, let's say, around the 10,000 or more. And we include data from several processes and experiments. And in many cases, this data has inconsistency. So the method that we use must take into account the way to propagate the uncertainties correctly. So here you have an example of PDFs, so at two different energies, and as a function of the fractional momentum X for different flavors. As you see, the PDF determination is not just the determination of one central value, but it requires the determination of the uncertainty. And this is the most important point of PDF determination. Not all flavors have the same uncertainty, and the uncertainty changes based on the kinematics and the momentum fraction region. And this is probably not a well-researched topic in machine learning. So how to treat the uncertainties, how to generate uncertainties from a given problem. So this is the peculiarity of this kind of problem. So NNPDF was born trying to solve and let's say optimize the problem by reducing all sources of theoretical bias, so avoiding the use of polynomials or fixed form functionals, and allowing the possibility to reproduce the non-Gaussian behavior which may be in the data. So for this we use neural networks instead of polynomials. And the second point is to provide a sensible estimate for all sources of uncertainties. The uncertainty can come from the data, can come from the minimization inefficiencies and degenerate minima, and also from theoretical uncertainties. So for this we use Monte Carlo artificial replicas, and I will show you in the next slide how it works. And finally, all the methods is tested with closure tests. So we check that if you generate artificial data, we can retrieve exactly the same input without adding any sorts of bias. So when we talk about parameterization, minimization, and stopping, we use neural networks, multi-layer perceptrons with this architecture 2531 with sigmoids and last layer linear. And for each parton, we allocate an independent parameterization. So in overall, we have 296 free parameters to determine. And this determination is performed by a minimization algorithm, which is, in this case, a genetic algorithm, which takes the chi-square and minimizes chi-square by comparing the data prediction to the PDF prediction, and you have the experimental covariance matrix, the inverse covariance matrix there. We use the genetic algorithm because we do not have to evaluate the gradient, and in this particular case the gradient evaluation is tricky because it depends on the process. You have to evaluate the backpropagation if you go for gradient methods. So the genetic algorithm is quite easier to tune in this particular case, and we have observed a good performance in our complex applications. Usually for the stopping, we use the training validation split. We iterate 30,000. We perform 30,000 interactions, and then we select the minimum. The best parameters are the minimum of the validation set. Now, for the uncertainty, if you look at this is an example of scatter plot with all the data points included in NMPDF 3.0 as a function of the momentum fraction x and the energy q square. We generate artificial Monte Carlo replicas, order 1,000 replicas, by sampling pseudo-data. So we take the original data and you shift it by multiplying the Kolensky decomposition of the covariance matrix to a Gaussian normal distribution. So in such a way we can, using 1,000 replicas, reproduce the original data set. So at the end of this procedure, we have several replicas, and here you have an example for the Gluon PDF. So each replica is represented by the green lines. And with these green lines, we can evaluate any observable or PDF-dependent observable by using the common rules for Monte Carlo sampling. So mean value to get the red line, and the uncertainty can be evaluated with the standard deviation or the 68 confidence level. And you can, in the parallel section, you have a talk talking about the phenomenological implications of this methodology in comparison to other methods. But I think this is a nice example of how we can apply all the methods of machine learning, including regression and the minimization of a genetic algorithm, to theoretical physics. Now, the second example that I would like to show is about the PDF for LHC recommendation. In this recommendation, the idea was to look at all the releases of global PDF feeds since the end of 2014. So I have an NPDF, MMHT, CTEC 14, and then develop a series of tools which are able to compress and reduce the size of this combination. Because the challenge that we usually have, and is the common problem, is that we have to decide how to combine the PDF uncertainty from individual PDF sets. Now, if you provide the 2 or 3 sets, there is no clear rule to explain how to combine them. And today, if you compare CTEC and NPDF and MMHT, you see that for a given observable like the gluon luminosity, the values are overlap in the region where we have data, but also in the regions of the extrapolation regions. So such kind of combination is possible. In 2011, the idea from the PDF for LHC working group was to just take the 3 providers of PDFs. Here you have an example for the Gluon Fusion Higgs production, and say that in order to obtain the combined prediction, you just evaluate the predictions for all the 3 sets, and then you take the upper and lower band as uncertainty. And you can understand that this choice was okay, acceptable, but over-conservative, because there is no proper statistical meaning of this procedure. So in 2015, we decided to change and to provide a statistical interpretation by delivering Monte Carlo and Hessian representations of this combination. So the idea is I take the 3 main providers and they build a prior which has the same statistical properties of the combination of these 3 global providers. So in simple steps, we generate a prior Monte Carlo with all the information from the global PDF feeds, and they must have the same data set, similar theories, similar big lab evolution equation. And then we apply reduction algorithms which may try to reduce as much as possible the redundancy inside this set of PDFs. And finally, we deliver the PDFs in Monte Carlo and the Hessian representation. So in this picture, you have the prior, the Monte Carlo combination, and then we apply the Monte Carlo compression, and you get this compressed Monte Carlo PDFs and the Monte Carlo to Hessian PDFs using the Hessian reductions. So now I will just go briefly through these three algorithms and just to show you how things work. One word before doing that is how to create the prior. We must use global PDF sets, or at least PDF sets based on the same data set, because PDFs are compatible. So you see this plot for the quark luminosity. The three global sets are in agreement. If we start adding PDF sets from different data sets, then there is a clear incompatibility on the right plot here. So you have the global in CTEC 14 versus the DIS only fits for HEP PDF and AVM. In terms of, in the next slides, I will use these keywords, but it's quite, just to summarize, the PDF4C prior is the main combination of the three global fits, which is a Monte Carlo set with 900 replicas. And then we generate the Monte Carlo compressed version with 100 replicas and two Hessian sets with 130 respectively eigenvectors using the Hessian methodology. We decided to generate Monte Carlos and Hessians because the Monte Carlo representation can contain non-Gaussian, can translate the non-Gaussian features which are important when you are going to very high X values, so when looking at BSM or searches in general. Meanwhile, the Hessian sets are useful for many experimental needs, for example, when varying when using the nuisance parameters. So this is quite useful, and also to preserve the maximum precision in the data region. The Hessian representation is always the best choice. When talking about the compressed, so the CMC PDFs, the idea is quite simple. We have a prior with several replicas, 900 replicas on the left, and the idea is to reduce the size of this PDF set to something much smaller with minimal loss of information. So we pass from this left image to the right one, where you see that from 900, for 1000 in this case, we switch to just 50. The replicas are different, but the central value and the certainty is the same. So we preserve the statistical meaning of this distribution. And this procedure should avoid the bias in the extrapolation region and also conserve the physical requirements like momentum symbols. And this is achieved by simply creating statistic estimators. We look at the four momenta of the distribution: central value, variance, skewness, kurtosis. We evaluate also the statistical distance, so the Kolmogorov distance, and the PDF correlations between flavors in multiple points in X. Then we use a genetic algorithm to compare and to minimize this loss function, which is just, again, a chi-square function by setting the value of the statistical estimator in the compressed set and comparing it to the prior. At the end of the day, after the procedure, we get the final results. So here you will see, in the case for the PDF for LEC15, the prior, the gluon prior versus the Monte Carlo compressed set with only 100 replicas. So we are compressing 900 replicas in just 100. You see the quality is quite good for the gluon, for the down quark, but also for the derivative observables like the luminosities and the quark anti-quark distributions. If you check the PDF flavor correlation, also here, if you do the difference between the compressed and the prior, you see that the differences are quite small. And the same if you look at the PDF observable correlation. Now, the second method is the Monte Carlo to Hessian approach. In this approach, we take always the prior, the Monte Carlo prior, and then we use the Monte Carlo replicas themselves as the basis for the linear representation. So we generate a PDF covariance matrix based on the a grid of X points, and then we apply principal component analysis to reduce this representation and provide the minimal set of eigenvectors which are able to give you the best PDF covariance matrix. Here you have an example of the delivery. After doing this PCA, we compare the prior in green versus the red dashed distribution, and you see that the quality is quite impressively good. So we have absolutely the same distribution for both. We can change the number of final eigenvectors, but the results are always Gaussian and quite stable everywhere. Also, when looking to the PDF correlation, the difference to the prior is quite good, so closer to 0, and also for the observables, the differences are very small. Now, just a justification why we need both methods, the CM2H and the CMC, because at LAC, if you take a high mass Drellian distribution, it's possible to find a Gaussian distribution, and in this case, the Monte Carlo 2 Hessian curve, which is in blue, is the best choice that you can make in order to reproduce this combined prediction. And if you look at the compressed version, if you take, for example, HCB rapidity beam, where the distribution is not Gaussian, the compressed version is much better because it's able to reproduce the tail and the peak. Meanwhile, the Monte Carlo 2 Hessian tries to generate a Gaussian which fits all the distribution. Okay, and finally we have the super specialized minimum PDFs, and this is just a further step after the Monte Carlo 2 Hessian. So here, instead of just compressing the prior replicas, we take a process, we evaluate the flavors and the kinematic X, which is useful for this project, and then we apply the PCA procedure again. So you generate orthogonal projections, and you have the eigenvectors. So this is quite interesting because if you take the PDF for the LAC prior with 900 Monte Carlo replicas, and if you consider the Higgs production process, you see that in overall you only require 15 eigenvectors to reproduce all the Higgs physics, and a similar number is observable to other priors like an MPDF 3.0 and HEP TH. So we are able really to condense and filter the minimum number of required replicas in order to reproduce our process. Here another plot showing the difference and how the eigenvectors grows as a function of the process. If you include the Higgs process, the number of required eigenvectors grows, but then there are other products and distributions like the W's and Z and the T bar where the number is not required, so you keep fixed. And this is quite good because you can really improve the evaluation speed of your computation. Also here we show that the Higgs PT and rapidity are really well described by the CM-PDF, SM-PDFs together with the priors. And the only breakdown of this methodology is when using a SM-PDF which goes outside the range of your process. So if you fitted the Higgs and then you use this SM-PDF to evaluate the jets at very high invariant mass, then in some circumstances you can see that the uncertainty is not good. But this is something very simple to fix. It's just add the process on top of your previous SM-PDF. Okay, so in summary, I wanted just to go through the PDF topic and show you that this is one of probably the most interesting applications that we have been working in the past months, and the results and also the deliverables that the PDF community are generating are useful and are every day trying to achieve better and trying to create new techniques. So in future, we are looking at the integration of modern machine learning techniques like deep neural networks and in particular reinforcement learning in the PDF determination. And hopefully in 1-2 years we can get better and more advanced methods and propagate these machine learning techniques to other topics in machine learning, in theoretical physics. Okay, thank you for that.
So yeah, it's very nice to see that neural networks are also breaking their way into HEP TH. I'm curious about the error propagations. It's a very interesting topic.
Mm-hmm.
So right now, the error propagation in PDF, for instance, it's basically numerical propagation, like you do for many observables of uncertainty. But are there efforts to incorporate uncertainty like in the actual model themselves? Like for instance, there's like density, like a mixture models that can learn densities as part of the learning procedure.
Yeah, exactly. Yeah, as you say correctly, today we use this bootstrap procedure to propagate the data uncertainty to the PDF. But we are thinking about the usage of reinforcement learning and other techniques to incorporate, for example, the theoretical uncertainties. For example, today we can think about generate scale variations uncertainties, and then trying to propagate these fluctuations to the data, modifying the structure of your space, and then applying the genetic algorithm. And these are, I mean, the most is what we are trying to build now. No? And probably, yeah, I think that probably by the end of this year you can have some initial study about it.
Thank you.
Can you please go to slide 11? You generate your replicas according to a multivariate normal.
Yeah. Yes.
At the same time, you claim you make no assumption about the Gaussianity. How is this compatible?
No. Yeah. No, what we do is that we generate a large number of Monte Carlo replicas using this multivariate distribution for Gaussianity. But we are using the experimental covariance matrix to decide how to shift. So we are not modifying the data uncertainty before doing this procedure. So this is what I wanted to mean. So if you get an experiment where the uncertainty is not symmetric, not Gaussian, this procedure will keep it non-symmetric, right?